This is part 2 of my review for the chemistry exam coming up pretty soon here. And this is going to cover, of course, in the older editions, chapters 1 through 3, 4, 5, and 6 editions, and then chapters 1 and 2 of the 7th edition. So 7th edition users, don't look at chapter 3. This is not relevant. So let's review atomic theory very quickly. I'm not going to say everything that I said in lecture necessarily because I want this to be pretty quick. Just a couple of the most important things. So all matter is made of atoms. We said that a number of times. This is based off of Dalton's theory. This was established a long time ago. Atoms are the smallest stable building block of matter. Protons and neutrons, which make up the nucleus of an atom and where most of the mass is, each one of these little subatomic particles, protons and neutrons, weighs 1 atomic mass units and live in the nucleus of an atom. So like I said, most of the mass of an atom is in the nucleus. The vast majority of the mass is in the nucleus. Electrons weigh approximately 1/10,000th the mass of a neutron or proton. That's why they don't really factor into the atomic mass of an atom because they're just so much tinier compared to protons and neutrons. And of course, if protons and neutrons live in the nucleus and the electrons are orbiting around the nucleus, these are eccentric orbits. They're known as orbitals. We talked about some of the shapes of these things. And later in this review, we're going to look at electron configurations. So let's start with a little review of isotopes. And the basic definition, the simplest definition that I can give you is same number of protons, so therefore same element, different numbers of neutrons. So let's do a bunch of examples of isotopes, starting with one of the simplest. The way we write isotopes, of course, is we give the chemical symbol, and in the upper left-hand corner, we give the mass number, and on the lower left, we give the atomic number. Now, if you ever get these things confused, remember the mass number is always going to be bigger than the atomic number, except in this case where they're equal, but nonetheless, the bigger number is usually the mass number, and the smaller is the atomic number. And by convention, once again, we have to be careful about where we put these numbers. So let me just remind you that the mass number is always the upper left, and the atomic number is lower left. That's if we're writing isotopes on paper. We're not talking about the periodic table here. We're just talking about writing isotopes. An alternative way of writing this isotope is just to simply say hydrogen, and then you just put a -1 like so. The 1 means the mass number. Hydrogen is always going to be atomic number 1, so there's no need to specify the atomic number. Versus something like hydrogen 2, this really does exist. The mass number is 2, and then we would write this as 2, 1 like so, and there's hydrogen 3, which we would write like so. Okay, so 3 isotopes for hydrogen. By the way, these isotopes, I think this is the only isotope that I know of that has very specific names for these isotopes. This one's sometimes called protium, and that's your standard vanilla hydrogen. This is the most common type of hydrogen. This one's called deuterium, and this one's called tritium. Now, no other isotope, as far as I know, has special names for it. Generally speaking, we just write the element name -1 or -2, in this case, -3. And again, the way we write the isotope specifically is like so. So let's look at some simple cartoon pictures of what these isotopes would look like, starting with this hydrogen 1 species. Quite literally put, this one only has a single proton in the nucleus. I'm going to use red to indicate that it's a positive charge, versus the electron. There is only 1 electron that's orbiting around this nucleus, and its charge is -1. So we've got 1 positive, 1 negative. There's no neutrons in this species, and that's it for it. This is called the first shell, by the way. So first shell. Always the first shell is the closest to the nucleus. Let's move on to this species. So hydrogen 2, on the other hand, still has 1 proton, so you can't mess with the number of protons, because if you do, you're going to change the element. But it also has, let's use a different color. We'll use green, I guess. Also has a neutron in the nucleus. And that's the difference between this first species and the second one. But there's still, nonetheless, there's 1 electron that's orbiting around the nucleus. Now, the third species still has 1 proton. Nothing's changed about that. But now we've got 2 neutrons. This is our simple little cartoon picture. And then, of course, there's 1 electron. Some other isotopes that we commonly run into. Here's carbon. So carbon is carbon-12 in this case. We're talking about very specifically carbon-12, that isotope, versus carbon-13 versus carbon-14. Okay, so this carbon has 6 protons. This one right here, so 6, I'm going to label this 6 protons. I'll abbreviate P for proton, and 6 neutrons. This one still has 6 protons, so nothing's changed about that. It's still carbon, but this time we're talking about 7 neutrons. And then finally, this one still has 6 protons, but 8 neutrons. So that's what isotopes are. So every element in the periodic table has at least one isotope, and the difference between isotopes is it's the same number of protons, but different numbers of neutrons. So I do have questions related to this, and all you have to do is figure out how many protons, neutrons, and electrons given an element. I may have you fill in the blank, that kind of stuff. It's a pretty simple question as long as you understand how to do this. Now, the way I'm calculating the neutrons, of course, is the way you quickly get that is you take the mass number minus the atomic number. So the bigger number minus the smaller number gives you the number of neutrons. It's a very simple calculation. And of course, back to these carbon species, if you've got 6 protons and we're assuming neutral carbon, which is a good assumption for the first test, we're going to have 6 electrons for each one of these as well. So 6 electrons. Whoops, I didn't mean to do that. I meant to put a 6 here. So 6 electrons, 6 electrons, 6 electrons. Okay, very simple question, easy stuff. So let's look at the periodic table now. And of course, roughly the same information is given in the periodic table. Let me just draw a very crude square out of the periodic table. And we'll just look at hydrogen for a quick second or two. So here's hydrogen. Typically speaking, though, the atomic number, which is 1 for hydrogen, is either in the upper right-hand corner, middle, or upper left-hand corner. So be careful. We're used to, when we write hydrogen just on paper, not on the periodic table, we usually put the atomic number lower left and the mass number upper left, but not true for hydrogen. And then also, you'll see the atomic mass in atomic mass units down below. This is 1.008. That's a typical value for hydrogen. And keep in mind, too, that this is not the mass number. It's not the same thing. It is called the average isotopic mass. So notice that it's not perfectly 1, as opposed to this isotope where it is perfectly 1. This is a specific isotope of hydrogen. This value is an average of all the isotopes, and its average isotopic mass is 1.008. And this is coming from the fact that hydrogen-1, this species, is the dominant species in a given sample of hydrogen. Now I can take you to carbon here for a second too. So here's carbon. Carbon symbol, of course, is carbon. It's carbon with a C. And its atomic number is 6, and just from memory, it's 12.011 atomic mass units for this, and this is also an average isotopic mass. And the way we get this the way we calculate this is we look at the percentages of the 2 common isotopes, carbon-12, carbon-13. This one's about 99% of a given sample. This one's only about 1%. And so when you do what's known as a weighted average of these 2 isotopes, you get something that's almost 12 because this is the dominant isotope, and the carbon-13 contributes very little to the overall average isotopic mass. Okay, these are specific isotopes. So this one's exactly mass number 12, so its mass is 12 atomic mass units. This is a specific isotope. It's carbon-13. Its mass is 13. And then when we just take a given sample of carbon, just any old sample, its average isotopic mass is 12.011. So that's a key difference between the periodic table and just simply writing specific isotopes on paper. I'm going to give you one more. One of my favorites is this one. So here's bromine. Oh boy, I forget the atomic number for bromine. Oh dear, I should have looked this up beforehand. I'm just going to put a question mark here because I forget what the atomic number is. But I do remember what the average isotopic mass is. It's 79.9 atomic mass units, and that's due to the fact that the 2 common isotopes of bromine are 79 and also 81. And this one is about 50%, and this one's also about 50%. So the average, the weighted average between these two isotopes is about 80. Okay, so this is 79.9, maybe a little bit more of the 79 one, but they're about 50-50, and that's why the average is 80. But really, as far as I know, the isotope bromine 80 does not really exist, or it's not very abundant. And so this is the average right here. Okay, so that's a key difference between the isotopes and the periodic table. Keep that in mind. We're still talking about the periodic table, and so the groups are the columns in the periodic table. They're also known as families. I don't think I mentioned this in class, but groups are families, the columns. The group numbers, you'll see that there's numbers up top. Every column is a number at the top. It starts at 1, ends at 18, and that's due to the fact that the first two groups are called the S block elements. It's 2 wide. The middle part is called the D block. That's 10 wide, and then the last 6 is another, that's a grand total of 18, and that's called the P block. Some of the groups have names. So, of course, we talked about in class, Group 1 are called the alkali metals. Group 2 are the alkaline earth metals. Group 17, jumping across the periodic table, are the halogens, and Group 18 are the noble gases. The rows, which we don't talk about as frequently as we talk about the groups, but the rows in the periodic table are called periods. Why are groups so special? Because they group elements by chemical and physical properties. So we saw, for example, that the group 1 elements, I gave you this demonstration in class, they all react violently with water. So that's one property of them. And you can't find these in nature because of that little detail, that physical property, or chemical property, I should say. Group 2 also reacts with water, although not so strongly, but that's why you can't find those in pure form. Now, the halogens have similar properties. We're going to see that they all pick up 1 electron to form a -1 charge, and the noble gases all have similar properties in that they're non-toxic, they're non-reactive, all kinds of stuff. Okay, so groups are very important when it comes to chemistry. So now, finally, let's start talking some electron configuration. So this is going to be a part of the test. I'm always surprised how many points people miss on these things, because really once you get the hang of it, it's not so hard. But the way that the electrons are organized around the nucleus, and this is organization. It starts with the shell. The shell is like the highest ranking layer of organization, and the shell starts at 1, and by definition, by convention, the first shell is always the closest to the nucleus. It's always the lowest in energy, and that's what's always true about that. We can go to the second shell, third shell, but this really goes out to infinity is the rule on this. Okay, so we can have, I shouldn't have put N here. What I meant to say is this goes out to infinity. The symbol for an infinity looks like this. Okay, so starts at the first shell, goes out to an infinity. And the further away you get away from the nucleus, the grumpier the electrons get, so they're not so happy. So they're happiest when they're in the first shell. But of course, we can only stuff so many electrons in the first shell, because the only thing that can exist in the first shell is called an S subshell, and S subshell can only hold 2 electrons total. But there's all kinds of different subshells. So there's S, there's P, there's D, and F. These are the common ones. These are ones that the elements actually can, the F one is kind of a rare one, but they have enough electrons to get to the F. G is kind of almost, well, I suppose we could still have G electrons, but you have to excite the electrons to get this far. But once we get to F, then it just goes in alphabetical order. We normally don't talk about F, G, and H, and I. We mostly focus on the first 3, and then sometimes on the F1 too. This is called subshells. Okay, they get letter designations. The shell number gets a number. Subshells get letter designations. And there's a pattern too that develops. So in the first shell, we can only have one possible subshell. It's called the S. In the second shell, not only can we have an S, but we can have a P. Third shell, we can have S, P, D, and you can see the pattern developing here. In the fourth shell, we can have S, P, D, and then F. Okay, and so on and so forth. This goes out to infinity. Now, the orbital is the trickiest one to talk about. An orbital is not a real physical object. It's just a region in space where the electron likes to hang out. And S orbitals always look like a beach ball. They're truly spherical objects, but when you take a cross-section of them, they look like circles like this, and the nucleus is right in the middle here. Okay, so S, always spherical. Really no direction to S orbitals. That's why they don't have any fancy subscripts and stuff like that. They're just beach balls. Now, P orbitals, there's one P orbital that's aligned with the x-axis, and that shape looks like a dumbbell. There's another one that's aligned with the y-axis, And that one also looks like a dumbbell. They all look like dumbbells. And finally, the third one is a Z, and that one's aligned with the Z axis. So there's always 3 types of p orbitals. If you're interested, the way we distinguish between these is p sub x, p sub y, and p sub z. That's the lingo that we use for those 3. But they all have the same shape. They just are orientated differently between them. Now I can go on to d. So there's 5 types of d orbitals. And I don't want to get into the designations for these, but trust me, there's 5. And each one of these, of course, once we talk about spin, can hold 2 electrons. So grand total for s orbitals, 2 electrons. If we entirely fill up the p orbitals, then there's 6 there. There's 10 for the d. And then by the time we're talking about f, we're talking about 14 possible electrons. Can fill that out. All right, so finally, spin. The only reason that we can stuff 2 electrons into an s orbital is because they're spin opposite, as we say. So these little arrows are meant to represent electrons. And if the arrow is up, we say that the spin is up. And if the arrow points down, it's called spin down or whatever. So it's only when they have opposite spins can they fit into an orbital together. Same goes for the p orbitals too. So each one of these p orbitals can hold a grand total of 2 electrons as long as they're spin opposite, like so. And of course, the d can do the same thing. And this is the basis for electron configuration. So this is how we organize the electrons. They're always going to have, every electron in any given atom is going to have a very specific spot where it's going to be around the nucleus. So imagine the experiment where we could pluck off electrons from something like carbon, and we're going to put them back. And so we have to put them back in the proper order. The order goes something like always the first shell first, because it's the lowest energy, and we go through. We won't have to go to infinity, but we have to go as far as it takes. And we start at the first shell, go up to the higher energy shells. So let's take now, so this is the basic description or the organization for the electron configuration. So now let's take a look at actually doing electron configurations. Remember, there's a couple ways we can get the electron configuration easily. This little diagram is one way, and I'm always going to give this to you on the test, so it's up to you whether you want to use this or not. I'm going to make a slight modification to this, and at the top of each one of these columns, I'm going to mention that 2 electrons per s orbital, 6 electrons per p orbital, and of course 10 electrons for d orbitals. So this is one way. The other way, and the way I do it mostly, is I use the periodic table. So I don't use this diagram anymore. I just look at the periodic table. The periodic table has that shape because of the way the electrons go. So, of course, electron configurations are like blueprints for building atoms. We're going to pluck off all the electrons, we're going to put them back, and this is how we specify where all the little electrons go. All right, so there's 4 common ways that we present the electron configuration. We probably start with what I call the normal electron configuration. That's just simply putting all the electrons into these little spots. Condensed, also known as the noble gas notation, that's a really easy way of doing things. And then orbital filling diagram, which is the most tedious. And then the good news is we can combine the condensed and the orbital filling diagram and make something that's fairly easy to do. So let's take a look at 2 examples and see how this works. It's pretty simple once you get the hang of it. So I just picked an element at random. I picked calcium. And the first question when you do an electron configuration always is to figure out how many electrons it has. So I looked up the atomic number for calcium, and it's 20, so that means that there's 20 electrons for neutral calcium. So our job is to fill out the electron configurations. So you'll typically see me write the Ca like so, a little colon like so. And then just simply put, if you're going to use this method, you start with the 1s. And of course, the s orbitals can always hold 2 electrons. But once you've filled 2 electrons in there, that's it. It's maxed out. You have to move on. And so we're at the end of this arrow right here. We move to the top or the next arrow down. We follow this arrow. We run into the 2s, and that holds 2 electrons as well. Once we're at the end of this one, we move back up here. We run into the 2p, and that fills 6. Remember, all the p orbitals can fill 6 electrons into that orbital. Then we get to the 3s. But I think, I know we're okay. I thought this was carbon for a second, so we have to keep going. So 2p, then 3s, 2. And then, let's see, 3p, if we have to. Yeah, we do. So 3p6, and then finally 4s2, and that should be 20 electrons. Let's just double check this. So 10, yeah, 10, 20. Okay, so that's what I'm calling the normal electron configuration. I will be asking for this on the test. So I use this diagram, but truth be told, I always use the periodic table these days. I don't need this anymore. And the way I look at this is calcium has 20 electrons I have to get to here. And the top row represents the first shell. And this is the S block. So this is 1s1. Helium is kind of an oddball. It's kind of almost in the wrong spot. Notice that I color-coded it S block. It really, in certain situations, can go over here. So it's 1s1. 1s2, and then you're at the end of this row, so you do like a little carriage return, 2s1, 2s2, and then you jump across 2p1, 2p2, all the way through 6, carriage return, 3s1, 3s2, jump over 3p through 6, and then carriage return 4s1, 4s2. So that's what I'm doing. I'm using the periodic table to my advantage. It's no accident that the S block is 2 groups wide. And it's no accident that this portion of the periodic table is 10 groups wide and this one's 6 wide. It has to do with the electron configurations. Now, of course, the condensed, so our job is to figure out which noble gas precedes calcium. We just back up in the periodic table. We get the argon. So argon is here. And what we're doing is we're condensing this electron configuration because now all the way through argon, the electron configuration is the same for calcium as it is for argon. All we have to worry about is the electrons past argon, and I've already goofed up. It's not 2s, it's 4s2. So here's argon. We do a carriage return, 4th row, so 4s1, 4s2, and that's all we have to worry about. Now the orbital filling diagram is pretty tedious. I'm going to try to go through this as quickly as I can. So we use electrons to symbolize the We use arrows to symbolize the electrons. So the 1s, once it's full, has an up arrow and a down arrow. We have to move on to the 2s. We're just following our normal pattern here, up here. It's pretty easy once you have the normal configuration. But the p orbitals, you've got to draw 3 of these. And remember, I told you in class that you have to time together. You will lose points if you don't do this. Okay, very important. I cannot figure out what people are doing when they don't tie them together like this. Okay, that's entirely filled out. Then we go to the 3s. And then the next P. I'm going to tie these together. That's entirely filled. And then finally we get to the 4s, and that's entirely filled. Okay, so this is called the orbital filling diagram. This is where we're showing all the electrons. Keep in mind, too, that Hund's rule says that if we're not going to entirely fill out this subshell, this p subshell, remember to space out the electrons before you pair them up. In the case of calcium, though, that wasn't necessary because the subshell, the valence shell is 4th, and it's entirely filled, so we don't have to worry about Hund's rule in this case. Now, what I like the most is this condensed orbital filling diagram because all we have to do is put that argon, and then all we're responsible for is the 4s electron. So just one line like so. 2 electrons go there, and that's it for that one. Okay, really slick, really easy. On the exam, I allow you fully to use this one, or you can do this one if you feel more comfortable doing it that way, but you're always allowed to do this too. So I'm really going to be looking for the normal, the condensed, and the condensed orbital filling diagrams. I want all 3, and you'll see that on the exam. Let's look at one more sample problem for electron configurations. I'm going to take you through the normal, condense. I'm sorry, but I think I'm going to skip the orbital filling. It just takes way too long. It's too tedious. We'll go to the condensed orbital filling. So the normal configuration, of course, the first question is to ask is how many electrons does selenium have? It's got 34 according to the atomic number. And so we're just going to go ahead and start doing this. So as always, you can use this little helper diagram or you can use the periodic table. I'm just going to start by saying selenium 1s2. I'm going to kind of move in a hurry because there's a lot of electrons to do here. 2s2, and then 2p6, 3s2, 3p6, 4s2. The trickiest part, if you're using the periodic table, is to remember to drop down a shell when you get into the D block that's entirely filled with 10 electrons, and then you pop back out with 4p, and we're 4 electrons into that. And that's it. So that's the normal electron configuration for selenium. Either way, you can use either a little helper diagram, the periodic table, or this helper to get this configuration. Now the condense is really slick because all we have to do is figure out the preceding noble gas. So here's selenium. Argon, once again, is the preceding noble gas. I'm going to start by writing it in brackets. So all we're responsible for is all the electrons past argon, which in this case there's quite a few. There's 2, 4s 2 electrons, 3d10, and then 4p4. It's pretty simple once we have the normal configuration already written out, but these are the electrons that are past argon. Those are the only ones we're responsible for. We're going to have to watch out for Hund's rule potentially for this set of p subshell electrons. Now let's skip over the orbital filling. Let's go right to the condensed orbital filling. So once again, argon, all the electrons are the same for argon as they are for selenium. All you have to worry about is the 4s, and there's 2 electrons that occupy that, and then there's, of course, 5 types of d orbitals. Remember, as I said in class, you got to tie these together. No tying, no credit. Okay, this is 3D. I'm going to put electrons here. This is entirely filled. And then the last set of 3 p orbitals goes something like this. Tie them together. This is 4p. Now, Hund's rule says that we have to space out the electrons before we start pairing up. So we spaced them out, and then we can pair up any one of these 3 with the other electron, but it has to be arrow down because they have to be spin opposite. But that's it. That's the configuration for selenium. And it's pretty simple to do it once you get the hang of it. So that's it.